What is a vector? A vector is an ordered list of things. And it's a very general concept. You can have a vector of anything, but let's not get fancy. Let's just talk about math. And you'll usually have a vector that is just a list of numbers. An ordered list of numbers means there's a first, a second, a third, a fourth one. So if you have 3, 4, 5 as your numbers, then 3, 4, 5 is different from 4, 3, 5. The order matters. If you've done any programming, computer programming, you'll be familiar with the concept of an array. An array is basically the mathematical type of vector. It's a list of items, and they have an order. And if you use the C++ programming language, they even call the special adjustable length array the vector class. That's why. So you've got a scalar, a vector, a matrix, and a tensor. These are all related concepts. Basically, a scalar is one number, a vector is a list of numbers, a matrix is a grid of numbers, and a tensor is a cube of numbers or more. So it's all lists of numbers in different sizes. I know tensors are more complex than that, but that's for a future video. So let's start with a vector. Let's say a vector is an ordered list 3, 4. Let's just have 2 numbers in it. Nice and easy. There's 2 different ways you'll see this. One of them might be this, 3, 4. So this is the way you'd write it on paper. 3 is the first one, 4 is the second one. You might also see this. You see 3 and 4, and the brackets like this with a T. T means transpose. Later on when we do matrices, you'll find out what transpose is, but basically it should be fairly obvious. You just rotated it. And the reason they do this is just because it'll fit on one line in the paper. They just do it to fit it on one line, but it's the same thing. So this is a vector. This is also a vector. Here's your graph. 1, 2, 3, 1, 2, 3, 4. So there's 3, 4, and your little arrow. So in this case, the list of numbers is coordinates. So you've got arithmetic vectors, or algebraic vectors, I guess arithmetic is better, and geometric vectors. And then you've got your vector addition and all this other stuff. I'm not going to worry about the geometrics too much, because the purpose of me teaching you about vectors is for AI later. But I may do a video in the future on geometrics if people are interested. Right now, let's keep it simple. So purely arithmetic, almost purely. So you can do math with vectors as if they were numbers on their own, special kinds of numbers. Let's say you have 3, 4, and 5 as a vector, and you add 1, 2, 3 as a vector. They have to be the same length because otherwise there's a void. There's nothing, not even a hole. So when you're dealing with vectors, matrices, and all this other stuff, the dimensions matter. You're adding a number, adding a number, adding a number. So what does it mean when you add these? Well, you add 3 and 1, you get 4. 4 plus 2 is 6. 5 plus 3 is 8. This is a more compact and easy way to represent it. So for example, let's say you had x equals 3, y equals 4, z equals 5, a equals 1, b equals 2, c equals 3. And then you wanted to say x plus a equals y plus b equals z plus c equals. You can see we're writing a lot of stuff down and it's taking a while. But it's nice and easy because, for example, this, we could say x equals, and let's put a bar on it. So we have x with a bar. Sometimes it'll be a little arrow, it'll be something. Sometimes they'll write it in bold, but it's to indicate x as a vector. And then this is y with a bar. So now we have x plus y equals, and this can be z with a bar. So this allows us to do math without having to write all this nonsense out every time. This can be a variable like anything else. A variable can be anything. So adding vectors is just you take each row and you add it, and that's your result. Subtracting is the same, you just subtract each one. Now the pieces in a vector are called elements. So 3 is the first, 4 is the second, and 5 is the third element. If you were doing a computer programming array, this would be, let's say this is variable a. So this would be, in programming, a0, then a1, a2. You might do that in programming. If you're doing it in math, we just use subscripts. So this would be 3, it would equal a1, 4 would equal a2, 5 would equal a3. Now I'm not writing the bars, and this could be 0, 1, 2 if you want. It's just whatever you want, but I do 1, 2, 3 when it's subscripts. You'll notice the bar is over a here, but it's not over a1, a2, a3. That is to indicate that these are scalars at a quick glance. A scalar is just a number, so 6. That's a scalar. Scaling. It's usually multiplied into the vector. That's why it's called a scalar. So if we take 6 times this vector, we just do each element, 6 into each of these. And you say, but I just said you have to have vectors of the same length. Yes, if you're doing two vectors, but a scalar is applying to each one. So if you had, instead of multiply, you had plus, then we just pretend this is a vector 666. That was an unfortunate choice. So it's just a shorthand. If we're applying a single number to a vector, a single number is a scalar, and we just do it to each one. And that's why it's called a scalar, because it's usually multiplied, and it's a scaling factor. It's this vector, it's 6 times this vector. So it'd be 6 times 3 is 18, 6 times 4, 24, 6 times 5 is 30, so you just get that vector. So vectors and vectors in math have to be the same length. A scalar is automatically applied to all of them as if it was a vector of the same length with the number the same for all elements. And that was what's called an element-wise operation. These are elements, so that's element-wise. And you can do any operation. You could do division, exponentiation, it doesn't matter. You just have to indicate somehow with proper notation that it's element-wise. It's just a list of numbers, you do it on each one, and there you go. So I don't need to go through every possible mathematical notation. Element-wise means do it on each one. So I'm going to have to slightly dip into the geometric right now, only slightly. Let's say we have a vector. Let's say it's our good old 3, 4. So here's 3, 4. And let's call this x. This is the vector 3, 4. X equals 3, 4. How long is it? Well, you may be familiar with the Pythagorean Theorem, a right triangle. So you've got a squared plus b squared equals c squared. It's the hypotenuse. The vector is the hypotenuse on these two axes. So we just use the Pythagorean theorem to find that. The notation, if we have x equals 3, 4, then the magnitude of x, commonly it's just 2 bars like this. You'll see absolute value. If you see a single bar, that usually means absolute value. So negative 3 equals 3 and 3 equals 3. It just strips off the sign. That's the absolute value. The magnitude of a vector is usually a double bar. Again, some people do different things, but that's usually what I see. So it is 3 squared plus 4 squared, but it's the square root because a squared plus b squared equals c squared. So c squared equals square root of a plus b squared. A squared plus b squared. So it's just here, I'll write it out. See, we just took the square and made it a square root, and there you go. And it's never negative because we're squaring both numbers, so it's always going to be a positive and we don't have imaginary numbers. So that's the length of this vector geometrically. Now, what if you have a longer vector? What if x equals 1, 2, 3, 4? Now we get into something called the Euclidean length, the Euclidean magnitude of the vector. It's actually the same thing. A squared plus b squared plus c squared plus d squared equals e squared. So you get rid of the square, take the square root. That's your magnitude. So it's the Pythagorean theorem with extra terms. And yes, that is for a reason. Geometrically, it's still right angles, it's just multi-dimensional right angles. That may break your brain, don't worry about it. It just works. You square all the terms, add them, take the square root, and there you go. So whenever you see the magnitude, you just square all the terms, take the square root of the result of the sum, and you're done. Nice and simple. Now there's something called a unit vector. A unit vector is if the magnitude equals 1. This may also be called normalized. If you've ever done computer graphics, computer programming, computer graphics, you'll have learned about normalized vectors. Basically, you want to say what is the direction of something, because geometrically a vector points and it has a length as well, but this is always 1. So let's say, you do some sort of calculation and you have a vector. There's a vector. It gives you a direction and it gives you a magnitude. Let's say you calculate the direction a character is looking. So you want to figure out where the character is looking and you want to see if they're looking at something else that's within a certain distance. You say, if they're looking at something that's within 3 feet, then they can use their lightning move or whatever. So you get your vector, and all you care about is the direction. You don't care whatever calculation you did to get the angle. It could result in a completely meaningless length. All you want is the direction. So you take the vector and you normalize it so that the magnitude equals 1. That's what we want. So how do we do that? You take your vector and you divide by its magnitude. And this is again a scalar. So if x magnitude equals 2, then you take x the vector, divide it by 2, which means you have a new vector, which is x1 over 2, x2 over 2, x3 over 2. It's just an element-wise operation. You divide the magnitude into all the terms. Now, does this make sense? Let's say we have our vector x equals x1, x2, and x3. So what is the magnitude of x? The magnitude of x is x1 squared plus x2 squared plus x3 squared, all of that square root. So now we want to divide that into this element-wise. So let's just do x1 first. So x1 divided by x1 squared plus x2 squared plus x3 squared. So that's what the new x1 is going to be. So the new x1 is going to be this. And x2 is just going to be a 2 here, x3 is going to be a 3 here. So the goal of doing that is to make this equal 1 on the new vector. So basically, let's replace the terms. So x1 squared, so we've got, this is going to be a big one, x1 squared plus x2 squared plus x3 squared, square root, over x1, but this is squared. So this is the new, and let's do a dividing line. This is the new x1. This is after normalizing. So now we're plugging it into the magnitude calculation again, plus x1 squared plus x2 squared plus x3 squared, square root, over x2 squared, plus x1, x2, x3, square root, x3 squared, and then a big ol' square root. So I've got the original x1 is just x1, x2, x3. Then we took this equation, we calculated the magnitude and divided it into all the terms. Then we're plugging it back in here, so we're squaring them, adding them, and square root again. We want this to be equal 1. That's the goal. If we succeeded, it's 1. So what do we get? Well, if we square this term, you square the top and square the bottom. So x1 becomes x1 squared, and we lose the square root underneath. So then we get x1 squared over x1 squared plus x2 squared plus x3 squared. We lost the square root here, and we added a square there, because we squared both. So we do the same thing here. The square is going to square into x squared, x2. This is getting confusing. And then the bottom is going to lose the square root. So x1 squared plus x2 squared plus x3 squared, we lose the square root, and then x2 squared. Same thing here, x3 squared. So we lost all the square roots on the bottom, and we squared all the tops. But these now have the same denominator, which means the fractions, we can add them together. So we actually have x1 squared plus x2 squared plus x3 squared. We just combine the fractions and add them together. But now we have the top and bottom of this fraction are the same. Something divided by itself, as long as that's not 0, equals 1. So we have 1. And what's the square root of 1? The square root of 1 is 1. So by dividing the magnitude element-wise into the vector itself, you guarantee that it is normalized, as long as the magnitude is not 0. In fact, it's going to be greater than 0 because it cannot be negative. We square all the terms and square root, it cannot ever be negative. It's 0 or greater than 0. Now, why can't we normalize a vector of 0 length? Well, which way is it pointing? If it doesn't have any length, you can't tell which way it's pointing. It's not pointing anywhere. It's a meaningless idea. So that's what a normalized vector is. That's how you take the magnitude of a vector. Now, why do we want this? Like I said, 3 feet, remember? So let's say we have whatever calculation we did resulted in this vector, which is the direction the character's eyes are pointing. We want to see if he's looking at something 3 feet away. The calculations we did gave us a direction, but the magnitude of the resulting vector doesn't mean anything. It's just accidents of calculation. So we normalize it, and then we multiply by 3, if that's the units of our world, 3 feet. So now we have the same vector going in the same direction. It's going in the same direction, but now, instead of whatever length, it's exactly 3 feet long. So now we could do collision math or whatever and trace that line for 3 feet and see if it hits anything. That's why we normalize. Now, there's only 2 more things we do with vectors. I mean, there's advanced, crazy math, graduate level that you do whatever with, but normal people like you and me only do 2 more things with vectors. That's the dot product and the cross product. So you have a vector x dot a vector y, and you have a vector x cross a vector y. And you'll see the cross product written with different symbols. It's usually a fancy X. Now, what are these? Once again, it's geometric, but it's not just geometry. I know at the beginning I said we're not really going to do much geometry. The way this is taught is usually usually geometric because that's where it makes the most sense, but I also use the dot product when doing AI, when doing neural network backpropagation training. And that has nothing to do with geometry, except it does conceptually, but not really. You don't really technically use geometry when doing AI training. So if you have 3, 4, 5, dot, 1, 2, 3. The result of this is a scalar. It's, first of all, element-wise multiplication. So you do 3 times 1 is 3, 4 times 2 is 8, 5 times 3 is 15. But then you add them. You square all the terms and you add them. So 15, 25, 23, 26. So this vector dot this vector is 26. Two things I want to point out. First of all, x dot x equals the magnitude of x squared. If x is ABC, then the magnitude of x is the square root of a squared plus b squared plus c squared, which is a times a plus b times b plus c times c, square root. See? A times A, B times B, C times C. But now we want to get rid of the square root, so we square it. Why is that useful? It's not. That's just for fun. But it does make sense when I tell you geometrically what this is. Let's say you have two vectors. You got a vector this way, and you got a vector this way. This is A, this is B. What is A dot B? A dot B equals the magnitude of A. I need to move this over. A dot B equals the magnitude of A times the magnitude of B times the cosine of theta. What is theta? It's the angle between them. There's theta. The purpose of the dot product geometrically is to figure out the angle between two vectors. And in the AI training, in the neural network backpropagation, the dot product is used to combine partial derivatives using the chain rule into factors up the chain. If that made no sense to you, wait for a future video. But geometrically, it's the angle between. So you'll notice we have the magnitude of A and the magnitude of B. So once again, this doesn't necessarily mean anything. Let's say we want the theta, so you have to calculate the magnitudes and bring it over, and then you do the arc cosine and you get the actual angle. But remember what I said about normalized vectors? If both A and B are normalized, then this is 1 and this is 1, so you just have cosine theta. And let's say you're only trying to compare to see if it's greater or lesser than. You don't care to actually find theta, you just need to compare, so you just do the cosines. I'm skipping past this a little bit. This is talking about optimizations in computer programming. When you're doing graphics, computer graphics, you want to be efficient because you're doing a lot of them and you want everything to be fancy and shiny and impress the user. So you have to do a lot of math. So if you can remove unnecessary math, you can do more math. So making sure A and B are normalized gets rid of that. Only comparing instead of actually needing the angle itself is another optimization. There's optimizations you can do, but geometrically it's this. And once again, as I said, if you have x dot x, let's say A dot A. So instead of B, this is A. So we have A dot A. Well, this becomes the magnitude of A, cosine theta. Well, magnitude of A times magnitude of A is magnitude of A squared. And then what's cosine theta? Well, theta is 0. There's no angle between a vector and itself. So theta is 0, and now we just have the magnitude squared. So there it is. So the dot product finds an angle between two vectors, and it also has non-geometric uses. The final thing is the cross product. We have A vector cross C vector. Geometrically, this gives you a vector that is perpendicular to the other two vectors. Let's say you have A and B. Well, C. Pay attention. C. A perpendicular vector is either pointed out of the board or into the board. And in this case, it's what's called a right-hand rule. A cross C. Point your hand along A. Curl your hand towards C. Curl your hand in with your right hand. Take your right hand on A, curl it towards C. Your thumb is pointing in the direction the perpendicular vector will be. And this is useful geometrically for many things. And I'm not going to go over what it is right now because there's a whole bunch of different ways to calculate it, and the easiest one involves matrices, and I want to do a video on matrices first. I'll just write it up so you at least see it though. So let's say you have vectors A cross vector B. To calculate that, you take the determinant, which is 2 bars. Yes, that is the same notation as absolute value, and yes, that is silly. A lot of times in math, you're going to find a situation where people have reused notations and they're confusing. You kind of have to just roll with the punches. They weren't really planning ahead to make sure it was nice and easy for people to learn. They were just doing math. And the general view, even, not every mathematician has an attitude. There's a lot of wonderful mathematicians. Brady does videos about them. But even the nice, wonderful mathematicians, a lot of the time are more concerned with with getting their math done than trying to be professors. So you'll just have to deal with the notation, but basically, let's say you have these two vectors. Let's say we're three-dimensional, so we have A1, A2, A3, B1, B2, B3. So it's the I vector, J vector, K vector, A1, A2, A3, B1, B2, B3. You take the determinant of that, and that is your cross product. I, J, and K are the unit vectors. This is a vector of length 1 along x. J is a vector of length 1 along y, and k is a vector of length 1 along z. The determinant, we'll do that later. That's a whole nother topic. The cross product, as far as I know, does not have a non-geometric use. Maybe there's something fancier I haven't encountered. So a quick summary of vectors is, it's an ordered list, like an array in programming. You can do anything element-wise, as long as they're the same length, and then you can do the dot product and cross product. If I ever get into computer graphics on this channel, it's going to be far in the future. So I don't expect to ever need to explain the cross product to you to use it. The dot product, I will, but the dot product's easy. So now you know everything you need to know about vectors. And while you absorb that knowledge, I'll be seeing you.